and welcome to where we take you on a live tour of a lab and get you up close to the science that happens in TIFR. With me is out here is a liquid nitrogen tank. That's a 5,000-liter tank. And behind that, maybe you can see the brown big tank. That's going to be the buffer where the liquid.
Liquid nitrogen tanks.
So these are let's start going inside, Vijay. Let's show them what happens inside here. So yeah, let's come in. So this
going
is a
high temperature is easier, but going low temperature is very difficult. In domestic fridge, we can go
yes.
to,
What is the at home you probably use a fridge, and essentially the way we work with low temperature fluids like liquid if you want to make liquid helium or liquid nitrogen, it's basically you have a fridge, but a more sophisticated fridge. But first, let's see a basic fridge over here. So you must have seen this is a standard two-door fridge. You may have seen with a freezer compartment and a normal compartment. Now, Vijay, how does this fridge work?
In fridge, there is a compressor. You must have seen compressor.
Yes, I mean the fridge advertisement always says that compressor with 10-year guarantee. So that's the compressor of the fridge, I suppose.
And the compressor compresses the refrigerant. It goes to high pressure as well as high temperature. That temperature is reduced by condenser coil, which is touching to the body. So if you touch the body, you can get hot, and that extra heat is absorbed in atmospheric air, and it goes to low temperature, room temperature, and then it passes to the capillary, where the and from capillary it is suddenly expand in the receiver, where the temperature drops. This expansion is called Joule-Thomson expansion, where the temperature internal energy is reduced. That is why temperature is also reduced to something -25, -30 degrees Celsius. That is utilized by our fridge components, and again hit back and goes to our compressor suction side.
So basically, the most important thing in this is that there is only one way in which you can cool a gas, which is by making it expand. So any fridge, what it does, it takes whatever material has to get cooled, which is the gas or the refrigerant that you call it. It is compressed. Now, when you compress it, its pressure will increase. If its pressure increases, its temperature also will increase. So it becomes a hot pressurized gas. Now, obviously, we don't want it to be hot. So we have to dissipate the heat somehow. So there are radiators, which is the back of the fridge or the side of the fridge. It feels hot because we are releasing this heat energy which was stored in this compressed gas. And then what happens inside, which is typically at the back of your freezer compartment, you have these little coils. You allow the compressed gas, which is now at room temperature, to expand. Now that means the gas is going to get cold. It's going to get cold, and well, in a normal fridge, cold means it gets to maybe about -20 or so, 25 maximum. And that cold then is what cools the freezer compartment. There's a fan that blows it into the normal fridge compartment. So the normal fridge compartment is perhaps at say 4 degrees or so, and where your freezer is -18 or so. That's the domestic fridge. Now, if you want to cool gases, if you want to liquefy gases, make them so cold that they become liquid, you effectively have to use the same idea, which is expand the gas to make it cold. This thing is also called a Joule-Thomson expansion. So sometimes if you look at it, you will see words like a JT expander or a JT stage. This just means it's a compressed gas that's expanding and becoming cold. Okay. So should we then see
so
yeah.
in the domestic fridge, we use JT expansion, but we have to go to minus 196 degrees Celsius to liquefy the nitrogen. So for that, we need some more efficient expansion. That is the expansion engine. Here is a piston expansion engine, works in Stirling cycle. So let us see how.
So there are many cycles. Okay, there are many different ways of what is a cycle you're playing with. Remember, we have to get back to this gas and compress it again and start again. So it's a cycle. So there are many cycles. What you're playing with is pressurizing a gas, doing something with it, expanding it, getting it back. So that's the cycle. The cycle is in pressure and temperature. Okay. So there's Stirling cycle, Brayton cycle, a lot of different cycles that are used in refrigeration, and we will see some of them. Now, we'll start with liquid nitrogen. What is liquid nitrogen?
Yeah, you can see liquid nitrogen.
So you have liquid nitrogen here.
Yeah.
Wow.
Okay. So this is liquid nitrogen. If I pour down, you can see how.
Can you see it in container?
Yeah, sure.
No. It is plastic. Yeah, just put some more in there. The thing that is boiling down is, yeah, you can see at the bottom of the container, there's a little bit of liquid nitrogen. The liquid, you can see it, just shake it to container, then we'll see the, not so much, just a little bit so that we can, yeah, you can now see the liquid at the bottom, it's boiling. And because the vapors that are coming out, nitrogen gas here, so cold, what you saw was clouds, because Mumbai is a very humid place. So we saw clouds condensing, and even when he was opening the tank of liquid nitrogen to sort of pour out stuff,
I'll show
there was lots of. Okay. So, there's a lot of moisture in the air, and it's going to form clouds once it becomes very cold.
Okay.
So that's liquid nitrogen. Its temperature is minus 196 C, or if you count from absolute zero, it's 77 Kelvin above absolute zero. So either 77 K or minus 196 C. That's the temperature of liquid nitrogen, and we're now going to see how it's actually made. Okay. So source of nitrogen, where do you get nitrogen?
Yeah, nitrogen, air contains 78% nitrogen.
Air contains nitrogen, so we don't need to buy nitrogen.
Yeah.
Okay, that's good.
So
We can just use the air.
Use source as the air.
Okay, so we start with the air.
Yeah, and we compressed air. So
let's go on.
Yeah. So I will show you a compressor. So this is air compressor, where air compressed.
Okay, so now we are at the heart of the liquid nitrogen plant, where air is pumping, and this is the
compressor.
So compressor. What?
It compresses air to 10 bar pressure.
So about 10 times the atmospheric pressure. The compressor, right? Yeah,
to remove moisture, we applied this dryer. So this is dryer.
Okay, so we will compress air, then you have to this will remove the water in the air. Okay, and it goes to 21%. So basically, 20% oxygen, 80% nitrogen.
Yeah.
What do we do with the oxygen?
Yeah, we remove oxygen in this PSA system. PSA system means pressure absorption string of absorption system. It has 8 filters. Say 8 filters. 4 filters are for purification, 4 filters for regeneration purpose. So you can see.
So what's inside these?
Yeah, inside this is charcoal molecular seals. So there are special type of charcoal that has controlled porosity. Nitrogen diameter is slightly bigger than oxygen diameter, and charcoal molecular sieves has controlled porosity that is only absorbing oxygen, and nitrogen goes straight away.
So let's get this again. So basically, there are these small column, we are going to make some special kind of charcoal.
Charcoal, yeah.
And this charcoal has lots of small holes in it.
Yeah.
So the huge surface area. And these micro sized holes are such that the oxygen molecules can stick there. But nitrogen molecules are slightly bigger, so they don't stick there. And the oxygen gets stuck to this thing, and then the nitrogen is going up. So, I mean, how much nitrogen is this? This is oxygen or something?
It get 99.8% purity.
99.8%
impurity.
20%.
Yeah.
3.2% is left.
Yeah, 0.2%.
So then
Yeah.
it gets after some time.
Yeah. So after saturating whole column, nitrogen flow backward and flush out the saturated oxygen. Meanwhile, this another set of filter is come into picture to purify the air.
Okay, so basically we have two sets of these filters.
Yeah.
So the nitrogen, the air under pressure, the dry air under pressure goes through it. Oxygen gets stuck onto the molecular seal. Nitrogen goes through. And after the 4 minutes saturated. So in 4 minutes, this is full of oxygen, can't absorb anymore.
Yeah.
So then what you do is you switch to the other set, which is going to absorb your oxygen, and in the same time, is this whatever absorbed oxygen, or how do you put it out?
With nitrogen only.
Okay,
we push it back.
Some of the nitrogen is used to push out the
Yeah.
So that just we just release it.
Yeah.
Okay. So then we have some gas which is 99.8% nitrogen.
Pure.
And where do we collect it?
And that is collected to buffer vessel because one you can keep doing continuously doing for every 4 minute cycle. 4 minutes that will yeah. The plant is running for 24/7. So
it's only switching today so that we can be here and show you the place.
Okay. Let me tell you, for producing 1 liter liquid nitrogen, we need 700 liter of gas. So our plant capacity is 77 liter. Our plant capacity is 110 liter per hour.
110 liters of liquid nitrogen per hour.
So
we need then
a
huge amount of gas.
I think 77,000 liter we need continuously. So that is why these buffer vessels are came in picture.
All these big tanks are storing the dry nitrogen gas.
And going to the.
So now we have from air, we have made dry nitrogen gas.
Yeah.
But it's still a gas and at room temperature.
Yeah.
So we have to now start liquefying.
Yeah.
So what is going to happen?
Here.
Yeah. So this is an engine with some cylinders.
Right. Exactly. This is a cryogenerator containing 8 cylinders, means 4 cylinders here, 4 cylinders there. And in this engine, there are 2 combination of pistons. So this work on Stirling cycle.
Wait, what do you have here?
Okay, I will show you how Stirling cycle works. Here is one piston, and here is another piston that is called displacer. In this gas chamber, if we put on hot water or hot chai, the vapors are hitting this plate and getting the area warm. And when it gets heated up, pressure increases. That pressure lift the piston.
Inside this, there is some displacer which is going to get lifted up.
Yeah.
Okay, so when this gas gets now you can see that there is a gap and it keeps moving. You can see there is this. You see the. Yeah, you can see the gap right now. The gap is on top.
Yeah.
And at some point the gap is at the bottom.
At the bottom.
Okay.
When the gap at the bottom, then piston is up.
So that piston is also connected to a smaller piston here. This is a little model of the Stirling engine.
Yeah.
And this piston then can move the here. So here you are using a difference in temperature
Yeah,
to make something move.
move.
Whereas what we are doing in the liquefier here is pumping this, moving, using the motion
Yeah.
to actually cause the temperature difference.
temperature difference.
So we are doing the opposite of this.
Yeah, yeah, yeah.
Okay. So I think it needs to be hot. Anyway, so I think we didn't see that there were two sets. So maybe we should take a long shot to show that there are actually two sets of cylinders on the other side. So there is one set of 4 cylinders on this side, and you can now turn to the other side, and there is another set of 4 cylinders on this side. Okay, so these are these working together? Or this is also one of them are working
together.
These are working together. It's not like the earlier one where 4 were working and 4 were not doing something
These
else.
are working
So
together.
8 of these are working, and they are effectively what is called a cryo generator, where let's just.
So I can show you, this is cryogenic section of cryogenic. Here is the piston, and upper thing, the white thing is a displacer, and piston compressor. Here the working gas is helium, because helium doesn't liquefy at nitrogen liquefaction temperature. So we need some gas which doesn't liquefy at this temperature. So this piston moves up and compress helium. After compression, helium goes upstairs through these water coolers. As we seen in liquid nitrogen, as we seen in refrigerator, there were condenser coils. Here, water cooler which cooled by chilled water, and after removing heat of this extra heat of helium, it goes through one component called regenerator, that is key component of this cryogenerator, and it goes to upper space, which is called expansion space. So you can see the model. Upper space is expansion space, and this is piston compression space. Gas compresses, then it goes to water cooler, then it goes to regenerator, then it goes to upper space and expand. When displacer come down, it uh, uh, expands the gas from small volume to large volume, and it rejects internal energy, which give low temperature, or it cool the gas. That cooled gas is coming back through regenerator, where it regenerator absorb its cold, and then it goes to compression space. So every time this regenerator will absorb the cold and give to cool down the next charge of gas. So at each and every cycle, the temperature will go down and down and down, and within half a minute, we can reach to minus 200 degrees Celsius. That temperature is absorbed by outside gas in this chamber, in this condenser header, and liquid, air is cooled and form liquid nitrogen.
The nitrogen
So
is cooled, yes.
condenser will.
So basically, the principle is the same. It's expansion of a gas that's going to cause cooling. Here we are using helium as the gas. Helium is being alternately compressed and expanded by this piston arrangement. That after a few cycles, the expansion place becomes cold enough. It becomes minus 200. Now you have to use a gas which will not liquefy at that temperature. If you want to keep going down, so we have to use helium for it. But that's a fixed amount of helium in there. And then, because it reaches minus 200 on the top, the nitrogen that is flowing past it will get liquefied, and then it is collected in these big tanks that you see here. So when all 8 cylinders are working, this thing can produce up to about 100 liters of liquid nitrogen per hour. Okay.
Yeah, right.
And liquid nitrogen is, of course, very useful for many experiments that we do in TIFR. So this is where we make liquid nitrogen. Now, is this the only gas we liquefy, or we can liquefy helium as well? Because some things we need liquid helium.
Yeah.
Okay.
So we have helium.
So the main challenge in this field was actually not to liquefy nitrogen, but to liquefy helium. And remember that helium will liquefy only at minus 269, about 4 Kelvin above absolute zero. And that is much, much more difficult than liquefying nitrogen. It requires a few tricks. In fact, so important that people got the Nobel Prize for actually working on such low temperatures, cryogenics as it's called. So shall we go to the liquid helium plants? Sure. Or are there some questions? Maybe this is a good time to stop and see if anyone has questions about liquefying nitrogen. Please remember that we cannot see you, we cannot hear you. So the only way you can give us your questions and comments is type them into the chat and we will take your questions.
Why do you want to have a dry gas?
What if there is moisture in the gas?
Yeah,
Well,
if moisture is good, yeah,
then we have a dryer.
Take moisture.
No.
Dry air. Why not have that filter also absorb?
Okay, then that charcoal molecular sieves are made for special purpose, and the moisture will degrade that charcoal molecular sieves. So before that, it is better to remove moisture. Otherwise,
first dry it and
efficiency
then
of
send
that
it to
oxygen separation will be goes down.
and you can't afford to have moisture after that because it would form ice
Yeah.
and then block everything.
Yeah.
Okay. So good question. Very nice question. So we first dry, then we remove oxygen, and then we compress,
Yeah.
and we cool.
Good.
Okay. Any other questions?
Can you tell us more about how exactly this engine works? One more time, like the electrical motor and the other stuff.
Okay. So this is 50 HP electric motor. Then there is a crankshaft which maintain the phase differences of this piston and displacer positions. Then uh, uh, piston compress the gas, helium gas, working gas. Then it goes to water cooler where the extra heat is removed, and then it goes to
Monitor the pressure of the working
oh, that side, that side.
So you always
Yeah,
monitor the pressure of
yeah,
the
yeah,
working
yeah,
gas.
yeah. And this is connected to PC. PC also shows the pressure cycles. Okay, and then it goes to
And how you the gas is start working gas.
helium gas. Is in closed cycle. Once we feed it, it will remain there only. It will just compress and expands. So after that, it will go to regenerator. I will show you regenerator. Then you will get a better idea. So this is regenerator sitting here after water cooler. So this is water cooler, and then again at top upper space. Yeah.
You have
And-
basically a two concentric tubes.
Yeah.
They are separated by
In between this passage, this is absorbing cold and giving cold to next charge of gas. So this is nothing but porous material. This is stainless steel, porous stainless steel. I have made cut off section to see the. So this is a very important thing. Some oil is carrying with this, and yeah. And its efficiency comes down. If its efficiency goes below
This is a
80%,
piece of porous steel.
yeah.
This is stainless steel, but it is porous.
No,
So the gas can
we,
go through this.
yeah. We developed this regenerator. These original regenerators are of wire mesh, means stacking of number of wire mesh layers. Here we developed this regenerator by powder metal, by additive manufacturing process by 3D printing. So this is 3D printed material. And it also gives very good efficiency. The most costliest part in this plant is the regenerator. So we developed a regenerator for our own.
So this is very clear.
Yeah.
designed and patented here. Is that correct?
With some other company for 3D printing. So
The idea is novel that one can use
Yeah.
3D printing
Yeah.
to make structures which are like this, which are actually porous, which have holes in them. Because you cannot machine this from a block of steel. So you could actually make this by 3D printing. And this is such that it's like a steel block, but then gases can pass through it.
Yeah.
And that's the heart of the regenerator. Earlier, they used to do it by taking wire meshes and putting them together. But this is a much better way of doing it. And this is the heart of the system over here.
Yeah, my boss, my section head, Professor K.V. Srinivasan developed this and designed and make further work on this. Okay, so after a regenerator, it goes to expansion space where the displacer come down and gas expands. When gas expands, its internal energy is rejected and temperature come down to some 40-50 degree, and that cold is absorbed in regenerator, and that cold is utilized by next charge of gas. And every cycle, this temperature is coming down and down, and within half a minute, this temperature is to minus 200 degrees Celsius.
And where does the nitrogen gas come?
Nitrogen gas is coming from so here is the nitrogen gas.
This is a gas inlet
Yeah,
from
and this is gas inlet from here.
from your filter.
Yeah.
Gas enters the system.
Yeah.
This.
Yeah.
And what is the pressure?
It is 10 bar, 10 bar
And the
pressure,
flow rate?
and flow rate is say 77 thousand liter per hour. And here is a condensed liquid nitrogen and filling the tank.
That's collected in
Yeah.
this.
Yeah. This is vacuum jacketed pipeline. And even evaporated gas is also coming back to condenser header to liquefy this. So shall we go to the our
Okay, so let's go to the liquid helium plant then. Okay, so now we're going to move from the liquid nitrogen plant to the liquid helium plant, which is one of the very few such plants, right?
Yeah.
In India at least.
Yeah. So helium temperature is minus 269 degrees Celsius, or just 4.2 degree Kelvin above absolute zero temperature. So helium liquefaction is more challenging than liquid nitrogen. In this, instead of
and helium is of course much more expensive. We have to buy the helium gas.
Yeah, it is much more costlier, and it is unique unique gas which doesn't solidify, and
So you cannot make solid helium. It can
Yeah.
only be liquid.
yeah, it will pure. But he has another unique property that it can show superfluidity. That is also a unique property.
Yes, which is a very strange thing. You can keep liquid helium in a glass or something; it will just flow out by itself. Which is helium. Liquid helium has some very strange properties. We won't get into that today. But again, I think the process is going to be very similar, except differences in how this compression expansion is done to be able to cool it so to make it so cold. So yeah, let's start. Where do we start?
So here is the helium plant. In this, we use expansion engine as a turbine expansion engine, turbo expansion. These vertical heighted things are turbine expanders.
So there you had a piston that was compressing and expanding, compressing and expanding. That is one way of doing it. In this case, what is used is called a turbo expander or a turbine expander. This basically has, imagine a place where you have something with lots of blades, a fan, okay, a stick fan. Now, the fan at home, it rotates how many times a minute? Maybe 100 times a minute, 200 times a minute. right? But this one, the blades rotate very, very, very fast. How fast?
2 lakhs rotations in minute.
So 200,000 times a minute is the speed of this turbine. And what happens
So
is,
these are turbines.
so the turbines are
turbine
over
and
here
second
at the top.
turbine.
Okay.
And these are various walls. This is called cold box of liquid helium. And these are various walls which are actually sitting here. But whole box is thermally insulated because we need to play with minus 269 degrees Celsius. So to insulate outer heat, we need to make it super insulated, vacuum jacketed. So walls are sitting somewhere here and operating from here. These are pneumatic control actuators. Yeah. Some are controlling the gas, some are just open and close. So you can see here the percentage of openings. Now plant is running. So you can hear the sound of plant. Okay, let us start with compressor.
Yeah, but let me just tell you what is happening in this turbine expander, because that is the heart of the system. So you have something that's got a lot of blades rotating extremely fast, 200,000 times a second. Now, remember, the gas molecules are also they're randomly moving, but when they get hit these blades, which are traveling so fast, they get knocked into a particular direction. And they
Tangentially.
Tangentially. So they get knocked, and then they go from a region which is high pressure to a region of low pressure. So that's how the expansion happens, and that's how you can cool it. And this works also for helium. These molecules get hit by the blade, they get additional velocity, and they're thrown in a particular direction where they are in a region of low pressure. So that's how this turbine expander in a very simple way works. But yes, we can start off from where the gas starts. So the helium is coming from outside the building.
Yeah.
It first
You are
comes
saying
to
that storage vessel. From storage vessel.
I don't think anybody can see the laser on the. Okay.
So from storage vessel, helium fed to the compressor. This is helium compressor, which runs with 230 HP motor, and it gives 20,000 liter air per minute.
Helium.
Helium per minute. So this is very high quantity of gas is giving by screw compressor. Then it goes to gas management panel, where the moisture and oil stresses are removed from gas, and it will continue controlled pressure and controlled flow gas to cold box. So this is basically filter unit and control unit for maintaining pressure and flow. So this is line drive for impure gas. This is line drive for impure gas. And we'll come later to this.
So you have lots of filters.
Yeah. Yeah. Because in this, we need to rotate very delicate turbine at very high speed, say 2 lakhs per rotation per minute. So in that case, if any impurity or any water molecule come in,
any bigger molecule, a heavier molecule, right? Helium is a very light molecule.
Yes, whatever gas,
some common gas coming in. Remember, oxygen might be, almost 16 times as heavier as helium. So those molecules can actually play havoc with this turbine at this very high speeds.
Yeah.
So we have to ensure that we remove everything, and it's only helium that can come in over here.
Yeah.
So
because any other gas will come, it will freeze and dash like a rock. So it will damage turbine, and turbine is very costly, something 50 lakhs rupees per turbine. So
is it similar to the process there, or is it
yeah, similar, but the purity rating is more in this. And this is a bigger compressor than that.
So it's not like helium leak tight or something like that.
Yeah. It's helium leak tight, right. Their air loss was not big. Yeah. But this system should be very leak-proof. Okay, so we'll show operating system.
Yeah, we can probably try and see how the system operates. Of
So-
course, everything, you don't operate anything by hand anymore. It's all operated through a computer interface.
Yeah. So
That's the wrong thing.
sir, okay. Hold on. This plant is connected to various gauges, the pressure transducer, temperature transducer at different locations, and all are connected to the PLC panel. Here is a HMI unit, and then it's connected to PC. So we can monitor every parameter here. So here you can see all the parameters like pressure readings, these are fine RPM, it is in RPS, and liquid levels,
Bingo.
liquid level is here, then return pressure, everything we can monitor here and control here, and this is control panel where we can switch on, switch off the plant. Even we can get access of this PC outside, and we can control it from outside also. But there are some walls necessary to work physically.
Just go back to the other screen.
Yeah. Yeah.
So basically, these two things are your two turbine systems, expanders. And I also see that you have an option to cool it earlier with some liquid nitrogen.
Yeah.
So you can sort of, I guess,
Yeah.
make the process a bit
Okay,
easier
okay,
by
okay.
starting with a colder gas.
Okay.
So do you sometimes use liquid nitrogen to pre-cool the helium?
So first let us see how the system works. So this is incoming gas, which cools down with series of heat exchangers. These are heat exchangers, and the incoming gas is coming through this and divided into two pieces. 20% gas straight away goes for liquefaction, and 80% gas is going for expansion in turbine. So here is the turbine expander, which expands the gas and then cool down this heat exchanger and go to second heat exchanger. Here it gets 200 minus 200 degrees Celsius, and then that cold is absorbed by this heat exchanger, and then further gas go to second turbine where the gas cool down to minus 263 degrees Celsius. After 263 degrees Celsius, pressure is almost atmospherically. Then it get back to return gas, and this cool all heat exchangers. That cold is utilized by incoming helium gas. Now this 20% helium gas is coming straight away to here, and through heat exchanger it goes to JT wall. This is Joule Thomson wall, like that our capillary in the refrigeration tube, refrigeration domestic refrigerator. Here gas is expand further. Before this heat exchanger, the temperature gets something 7 degree Kelvin, and here it expands to 4.2 degree Kelvin, where the liquefaction has done and collected in this tank. That is that tank. Helium storage vessel. The capacity is 5,000 liters per hour, and plant
5,000
production 5,000 liters per hour.
Not
And-
per hour. 5,000 liters is what this can store.
5,000 liters.
How much helium can you
And
make per hour?
helium capacity is 65 liters per hour.
65 liters an hour.
Per hour. Yeah.
All right. And
Then,
how many liters do we make sort of every year or every month or something like this?
Every month earlier, we when gas storage was sufficient, we could make 3,000 to 4,000 liters.
3,000 to 4,000 liters every month. Okay. And so this gas is then filled in all these smaller tanks, I
Yeah.
suppose, and people take them for their various experiments.
Yeah.
And of course, helium is super expensive. So unlike liquid nitrogen, which you can just waste, you cannot waste
Yeah.
the helium.
Yeah.
It
So,
comes back.
And
So all these labs have lines which take the gas,
Ah.
the helium gas, and they return it to the
Okay.
plant.
Yeah.
And is this, I guess, are those balloons where you store it?
Yeah. So all recovery gases come here and collected in these balloons, and these are 30,000 liter capacity balloon.
30,000 liter balloon.
30,000 plus 30,000, 60,000
60,000 liters.
capacity is there.
Okay.
And this is at atmospheric pressure.
Hmm.
And when balloon fills up, we start this recovery compressor. It's done automatically. There are recovery compressor. So these are recovery compressors that pressurize the gas and put back to helium cylinder. So
Try our best not to waste any helium.
Yeah,
So
yeah.
how much helium do we recover? 90%, 80%, 50%?
something 85%.
85% of the gas we can actually recover. Okay.
See, liquefaction of 1 liter helium need 800 liter of gas.
Mhm.
So 1 liter liquid helium evaporation is creating 800 liter of gas. So every transfer or transfer to your system, everywhere the gas heat up, and that gas is collected in the recovery. And
But I think it's pretty good that we can recover 85% of the helium.
so all labs are connected with this pipeline, recovery pipeline.
And are these, these containers in which we store the, and I see people walking around with these.
Yeah.
I mean, is this full of liquid helium or is this mostly, is it like a thermos flask or what is this?
Yeah. Preserving the liquid is also very challenging. So typically these are containers where helium is stored. But whatever we are seeing is just outside jacket. Inside vessel is, I'll show you a open portion. So actual helium vessel is here inside this. This is helium vessel, and this is whole jacket. So this is vacuum jacket like our thermos flask, and the thermos flask is having glass mirroring or silvering, so the highly reflected surface. So here we need better reflection effect. So we provide super insulation mylar, which are highly reflective and put layer by layer something 50 to 100 layers of super insulation milers, which reflect back radiation heat and preserve cold. And
Actually, the tank inside is much smaller. Most of it is insulation.
up to this to this. And one filling tube is directly connected to a jacket. Means it is directly conduction source for the low temperature to
Directly.
yeah. Uh, So this tube is having conduction loss. So this tube is keeping as long as possible and as thin as possible. Okay, so this is thin wall tube with extra long, and now you can see copper disc that are radiation shield that trap the radiation heat.
So these are
These are
radiation shields.
radiation shields.
Multiple copper discs that are there. Okay.
I can show you some photographs of things. So this is cold box, and this is compressor, the top section. This is how the screw compressor works. This is high pressure gas outlet. Then these are going to gas management panel. Then it goes to cold box, and cold box containing this type of heat exchangers, counterflow heat exchangers. Incoming gas is cooling down with return gas. Then then flow divided in two parts. One part is going for expansion, and this is turbine expansion. So a small tiny wheel is rotating and cooling down the gas. And first turbine goes to minus 200 degrees Celsius. Second turbine is going to uh, 10 degree Kelvin or minus 260 degrees Kelvin. Then this incoming high pressure gas expansion, Joule Thomson expansion and liquefying continue. And this is the return gas going back to compressor. And this is how the turbine works. This is turbine and speed is very high. So it runs on gas bearings. Initially, it is working rest on the magnetic bearing and then it goes on gas bearing. So this is how it runs. The rotation is 2 lakhs rotation in minute. This is stator of turbine, which provide tangentially heat of gas tangentially. So this is typically turbine. Okay.
Okay, so let's take a break here and see if there are any further questions on this. I will take the question on the chat after the session is over. We can definitely look at them. Yeah, now are we going to? It's almost 7:45. What's next? What are we going to do next?
Can we show what is happening to low temperature?
Yeah, we can do some nice experiments at low temperature. So yeah, we can, but of course we will not do them with liquid helium, right? Only with liquid nitrogen. Yeah.
With liquid.
So liquid helium, of course. Please remember that liquid helium. I mean, we cannot show you liquid helium. It's just too valuable and too important. The liquid helium that is filled in these tanks goes to various labs in TIFR. You can study superconducting properties, for example, of materials at extremely low temperatures. People use it to cool down various wires and make them superconducting, so they can be used for getting very high magnetic fields, superconducting magnets. For that matter, your MRI machine, in hospitals also will have to have magnets which require it to be cooled to very low temperatures. The NMR plant uses a lot of liquid nitrogen. We have a particle accelerator which has a linear accelerator. The linear accelerator has lots and lots of superconducting cavities and magnets. In fact, they have their own liquid helium plant because they almost, require so much liquid helium that this plant would not be able to supply them and the rest of the institute together. So they have their own plant. There are many labs in physics that require liquid helium for various purposes. Of course, liquid nitrogen is something which we can make internally out here, and it's much easier, much cheaper. Many labs which do not require liquid helium necessarily, but just want to make something cold down to minus 77 Kelvin or minus 196. For them, liquid nitrogen is good enough. And that, of course, we can do some experiments to show you what's happening. So you have some liquid nitrogen here?
Yeah.
And you're going to show us some things?
Yeah.
Okay, that sounds good. So there is liquid nitrogen. And the first question I'm going to ask people is, what is this smoke that we are seeing, these things? Please remember, this is not nitrogen. Nitrogen is a colorless, odorless gas. You would not be able to see nitrogen. What you're actually seeing, you can see the liquid boil over here. You just put it down. Yeah, there you can see that the liquid is boiling. Don't shake it. It's fine. We can see that it's boiling. And the cold nitrogen gas, when liquid nitrogen boil, it's going to create cold nitrogen gas. And once that gas comes in the air, and especially you can also see what happens when he drops it, it's going to take the moisture which is in the air around us is going to condense, and that's going to form clouds. So these are basically little clouds that were forming, clouds of water vapor condensing into forming clouds. Now,
we'll.
There is some question. Well, So is it possible that these balloons will get destroyed because of the fact?
Yeah. You can see, you can show the blue thing, that is relief wall. Once balloon reach to 50 millibar pressure, the relief wall opens and release the gas.
So the balloon can never get overpressurized. I mean, if it gets even a little bit overpressure,
That's
the gas is safely released. But hopefully, before that, we will not reach that place. We will actually take the gas and compress it.
This is about the average uptime of the machine here.
So are these machines working 24/7? Are they
This helium plant is running something 3 days in a week.
because that's enough right
in-
now.
Yeah, in two intervals.
Because we have the second helium plant, which supplies the LINAC as well. Yeah. So because we don't supply the LINAC anymore,
Yeah.
For the requirements of TIFR, it is enough that we can make a few thousand liters a month.
Yeah.
Okay.
Requirement also in gas gas availability also.
Okay.
So we run twice in a week.
We are constrained by non-availability of helium gas in the market.
Yeah.
And also the need. I mean, there is not that much need to make because you cannot just keep the helium forever. You have to use
See,
it.
helium is a escaping molecule. Once it went to gas, air, it just go above it.
I guess the person who is questioning is answered sufficiently now.
Right, and I don't think that he has a better liquid nitrogen or liquid helium plant which is more efficient than what we are doing because the plants are all very similar. So let's not worry about it. Now, one thing we said was that you require many hundred liters of gas to make a little bit of liquid, and that's because gases occupy a lot more volume, and when you cool a gas, it's going to become much smaller. And to see that, here is a balloon that Vijay has in his hand, and he is going to dip the balloon in liquid nitrogen. You can see the size of the balloon; it's just filled with air.
I'm
And
dipping inside
he
it.
is slowly going to dip it inside liquid nitrogen.
Can you show it on top?
And of course, we can see it show it from top as well. You can see that, of course, he's being very careful not to put his hands inside liquid nitrogen. That would be terrible. He would get
I'm just working.
he's just dipping the balloon inside the liquid nitrogen, and you can see the balloon is sort of getting shriveled and it's shrinking. It's getting smaller, getting smaller.
It just become flat.
And then it's become flat.
You can see
And you can
some
see some liquid inside it. There's some liquid inside it. As the balloon is warming up, it's getting, the balloon bursts.
Shall I do it
That-
again?
Well, we can try doing it again, yes, of course. Let's try another balloon. But you can see that as the balloon was warming up, it was expanding and there was a liquid inside the balloon. Now the question is, what is that liquid? Okay. Should we try another balloon? Yeah, we can try another balloon. Maybe don't make it so big so that it's great balloon. Okay, that should be good enough.
Okay.
Okay, so there we have a balloon. Let's try and make it cold. And as you can see, the balloon is getting almost
Balloon
flat.
become flat.
And
I can see some liquid at the bottom.
yeah, maybe you can just shake the balloon so you can see the liquid. Yeah, you can see the liquid is slowly evaporating.
You can see liquid. Now liquid has gone. Now
Now there's a little bit of powder outside. You can see this little powder inside the
you can see now powder.
powder, and that powder has also disappeared now.
Yeah.
So what was the liquid and what was the powder?
Okay.
And let me give you a hint that how did he blow the balloon? He blew the balloon not with room air, but with the air that he was breathing out. That should give you a hint as to what is the liquid and what is the powder.
Yeah.
So
Okay.
okay. So let's see if anybody has put anything in the chat.
Okay. Meanwhile, we will do some other thing. So, yeah.
What's liquid?
Okay. I have leaves. We just dip leaves inside. just what will just check. These are soft leaves. Soft leaves. When we dip inside,
Now you see the liquid started boiling very vigorously when he put it in because there were hot leaves
Now you
compared to the
can see-
liquid. And now,
we can crush like leaves.
could you hear the crushing sound? Let's maybe,
We can make fine powder out of this.
now what happened was the liquid, the leaf got totally powdered because of the low temperature. Now what was happening is, remember a leaf has, it's soft. Why is it soft? Well, of course, it's got water in the cells of the leaf. And if I dip it into liquid nitrogen, the water will instantly freeze. And then if I crush it, it's going to be hard and it's going to get crushed. Of course. Yeah. Okay.
Okay.
Now here is a rubber pipe. This is a rubber
Yeah.
or a plastic,
Plastic
pipe.
pipe,
It's a plastic pipe. It's quite flexible, right? You can bend it. You can see it's quite flexible. Okay. Now what something would happen when you put the pipe in the liquid? So here is the pipe, nothing inside it. Make sure you can focus on this part. So take a long shot, please. Take a long shot so you can see when we put it in, what happens over here. Okay. So when I put it in, some liquid is spraying out of the pipe.
Yeah.
And at some
Now
time it stops.
Now stops.
Now why did that happen? Why did that happen? We can do it again.
Just turn.
So what I'm going to do is you can now, this will help you find the explanation as well. This is the end I put in first. If it's become very cold, water ice is condensing on it. I'm going to take the other end now. I'm going to put the other end in, and again for a while, the liquid is going to spray out like a fountain here, and then it stops. Okay. So now you can tell me, or you can tell us why this is happening. Okay. Just remember, what did we do? It's a very hot compared to the liquid nitrogen. Liquid is at minus 196. Our plastic pipe was just at room temperature, so it is almost 200 degrees above the temperature of the nitrogen. So I put a very hot object in compared to the nitrogen inside it. So what happened? Well,
Heat up the liquid.
as with any, if you put a pipe inside a liquid, some of the liquid is going to go inside the pipe. But the sides of the pipe are very hot. That's going to make the liquid boil. And remember, we said a little bit of liquid because gas occupies a lot of space. So the gas takes a lot of space and it just pushes the liquid out, and the liquid sprays out of the pipe. That is what was happening. By the way, we didn't tell them about the first one, for the balloon. Remember, we blew the balloon with our exhaled air, and of course, the room air has about 80% nitrogen, 20% oxygen. We don't use all the oxygen. We use maybe 4% of it. So the exhaled air, what we blew out, still had about 15-16% oxygen. And when we blew the balloon with it, we cooled it, oxygen liquefies at minus 183. Nitrogen is minus 196. So it got cold enough that it liquefied the oxygen in the breath that was there, and that's the liquid. Now, of course, we have 2% carbon dioxide, and carbon dioxide, if you remember, doesn't really form a liquid, it goes directly to the solid state. So the powder you saw was dry ice. It was powdered carbon dioxide, which is why it just suddenly went off, because it just sublimed back into the gas. The liquid was liquid oxygen, again from our breath, and the carbon dioxide from our breath was the powder which you saw. Okay, any other little demonstration? The paper funnel. Yeah, so what did we do? We took a piece of paper, we folded it in half, we folded it in half again, and we're going to make a little funnel out of this. So we will just hold three pieces together here, and this is like a funnel where, a piece of paper, you can buy Helpuri on the road or something, and we're going to put some liquid nitrogen in it. So if we put some liquid nitrogen in it, look what's happening here. Something is dripping. We see something dripping from the paper, but the level of the liquid inside is not changing very much. Something is dripping out, and it's not forming. It's not water, because it's not collecting below. If it was water, there would be a puddle below. It's not water. There's no puddle below, but something is falling from here.
Yeah, you can
Right?
see,
And it doesn't. It just evaporates immediately.
Yeah.
So what is happening here? And look, there's still enough liquid nitrogen. I can pour it out. We'll just throw it out. See, there was all that liquid nitrogen. And well, maybe liquid nitrogen makes a hole in the paper. Let's check that. So let's just make the paper warm a bit, and let's open it up. Oh, there's no hole in the paper. So it was not certainly nitrogen pouring through it. What happened here? here is that again, there's a thin piece of paper. The size of the paper, the size of our funnel got really, really cold. How cold? Well, the temperature of the liquid nitrogen. Now, liquid nitrogen is below its boiling point, so it must be at less than minus 196. Air is composed of oxygen and nitrogen, and mostly just like when you take a bottle of water out from the fridge, water condenses around it, or a glass of cold water, you find some water droplets around it. Here, the paper surface is so cold that air starts liquefying.
Yeah.
Air becomes liquid and starts dripping down from it. So what you saw dripping down was liquid air, which is more concentrated in oxygen than in nitrogen because it's easier to liquefy the oxygen. That's what you were saying.
Let us show cooker that we can.
Oh, yeah, famous cooker. We use a cooker at home. What do we do to cooker at home? We fill it up, seal it, you put it on a source of heat, and after some time the water boils and it will start to rain. So now we have a cooker. Where is our cooker? First we just make a cooker. So here is our little cooker, which has a gasket outside and the weight on it, and we will put some liquid nitrogen in it. So I'm going to pour some liquid nitrogen in it. Okay. Okay, and now we're just going to put the lid very quickly. So, and it's starting to immediately.
So how the turbine works in helium? So this is how the turbine works. Let us see volume.
So you can see the liquid is boiling inside it, and it will blow up a balloon in no time. And it's extremely cold. There's ice forming outside it because something. But remember, the atmosphere is hot, so it boils the liquid almost immediately, and it causes the whistle to go off. So
what will happen if I press this whistle?
Oh, that's going to be very dangerous.
Yeah,
because then your cooker might actually explode. That's not a safety gasket. Well, the safety gasket might. No, because the safety gasket is designed for its hot. It's a piece of lead.
Yeah, it will not melt.
The lead will not melt in this case. So it's very dangerous. So you should always make sure that the whistle is operating. Okay. Zarin, do you have any electrical experiments? Something else to show?
Yeah, we have many experiments. We
Uh,
can
we
create
have
balloon.
we have 5 more minutes.
Vacuum. We can create a vacuum with liquid nitrogen. Yeah. Liquid nitrogen is used or low temperature is used to create very high vacuum, very precision vacuum. You can see a bottle means
So
liquid.
let's first explain what is there in the bottle.
Okay.
There's some red liquid here.
Huh.
And
no, this is just fancy thing.
That's fancy thing. So people
There are two bottles are connected with center tube.
And there's a little heart-shaped tube over here, a heart-shaped thing.
So I will pull down this upper vessel. You can see fountain is coming up and whole liquid come without against gravity. So upper vessel created a vacuum and liquid rushes up upside.
Now, why did this happen? Because remember, if you cool down a gas, it's going to occupy much less space. But then this is a glass vessel, so the space is the same, which means its pressure went down.
Yeah.
If the pressure went down, there's lower pressure up here than down here. So the liquid which was there rushed up and spit out like a fountain.
Yeah.
And it is the upper vessel. So this is like
upper vessel, whatever air was there, it's reduced to 700 times lower volume that creates vacuum.
Okay, so we have about 5 minutes more, and yeah, we can show one more demonstration. We have about 5 minutes more. We can maybe show the bulb. Yeah. Superconductivity. Yeah. So maybe we can just show that. So the other thing, and this is one of the reasons it was so important to reach these low temperatures, is because properties of metals, in particular their electrical properties, change drastically with temperature. So what we have here is a battery connected to a bulb and a coil of wire. Okay, and you can see the bulb is glowing. Now, of course, this coil has some resistance, depends on the temperature. Now, if we cool the coil, what's going to happen? Is the resistance of the wire going to increase or decrease? Well, if the resistance increases, less current will flow, the bulb will become dim. If the resistance decreases, then the one should become brighter. So let's see what happens. I'm going to dip this in liquid nitrogen. And oops. Oh, the bulb is getting much brighter. Right? You can see that the bulb is getting brighter because we cool down the coil. And as the coil warms up, if we warm up the coil, the bulb slowly going back to the temperature, the bulb will start dimming again. So this just shows you that the electrical properties of materials also change drastically with temperature. And here we saw that the resistance of copper goes down. Of course, there is still some finite resistance, but there are much more interesting materials. These materials are called superconductors. And a superconductor offers absolutely zero resistance to the flow of current. Now, superconductors have another interesting property, which is that they repel magnetic fields. They do not like, you know, they repel magnets. And what we have here is a little track. The track is made of magnets, and the little box you see has a superconductor inside it. It is being cooled by liquid nitrogen. And this superconductor actually becomes superconducting at something like 90 Kelvin, so which is above the temperature of liquid nitrogen. So hopefully very soon, once it has become cold enough, it will become a superconductor. And then it will, since the superconductor does not like a magnetic field, it repels it, it will float on top of the magnet. And this is called magnetic levitation. And that's what the demonstration is going to be about. It's going to be about magnetic levitation. It will take some time. It will take some time to cool down. Till that time, when it cools, it's also what that other material properties change. So here we have a light emitting diode and an LED which is yellow in color. Wait, let's first show that the LED is yellow in color. Maybe with the white background, yeah, that's good. So we can see that the LED is yellow in color. And now you put it in the liquid nitrogen and see what happens. Put it in the liquid nitrogen and whoops, do not show the camera in the liquid nitrogen. And you can see from yellow, it has now become green. So again, the properties of the semiconductor change, and as it warms up, the warm it up by blowing on it, it will go back to yellow. And pulling it down, it becomes maybe it's still on the side. Let's look at the side. From the side, it's easier. Yeah. It's green, and you should take it out and show it yellow. So let's make it yellow. Yellow. Wait, it's still not yellow. And you look at it from the side. There is nice diffusion. You can see the color. Okay, now it is definitely yellow.
Yeah.
And
Now
see,
I'm dipping, it becomes
yellow, and the yellow will slowly become green.
green.
Yeah, what you're seeing is a lot of ice on the side. Yeah, it's become green. Green.
Yeah.
Okay, by now let's see if a superconductor is cooled down.
Yeah.
Yes.
So this is magnetic track, and this is superconductor. Name is yttrium barium copper oxide. You can see the train is floating on the track. It doesn't touches to the track.
Can you put something
As the
between
track
the,
ends, they automatically
can you
come back.
put something in between to show that there is nothing between the,
So if I put something, train just run over that.
it is actually floating. You put a paper and just went over.
The magnet orientations are like this. These are north pole at the top. These are south poles. Again, last row is north pole. And two magnets sitting in different orientation to close the track. As the track ends, train automatically repel back due to this magnet. And if I try to turn this train, it back to track direction, it can go 180-degree, but never changes any other direction. It can go 180-degree only. So it maintains track direction. If I try to tilt it back, if I try to tilt it back to vertical, if I tilt whole track, then also it is standing to the track. We can lay vertical track, train can go vertical. In Mumbai city, there is no space left over. We can run the track along the building, train can go sideways of the building. Okay. For accident, there is another possibility. If I break the track, so train just stop there. It doesn't go further. It is very track sensitive to the track. So this is superconducting levitation. In Japan, Yamakasi, one train is running on same principle, which runs at 20 kilometer per hour. Okay.
All right. Okay.
That's it.
So I hope you enjoyed that little demonstrations with liquid nitrogen. And on that note, I must thank you, Vijay, for showing us the liquid low temperature facility where we make liquid nitrogen and liquid helium. And if you have questions, please remember you can always send them to us over email. Our email address is outreach, outreach at tifr.res.in. And this was just to remind you our special 5th Sunday Chai and Mai session, which is an online only one where we visit a lab in TIFR. We will be back to our regular programming from next week, first Sunday of April, where we will be at Prithvi Theatre to talk about some biochemistry on how we image fat molecules inside cells. So that's what's coming up now, and keep following us and join us for our program. Thank you so much for watching. And thank you, Vijay, for taking us.
Thank you very much.
Thank you.
Thanks, sir.